Out there, right now, in the darkness between galaxies, something is pushing. Something is stretching space itself apart, tearing the fabric of the cosmos like a sheet caught in the wind. And we do not know what it is. We have given it a name. We call it dark energy, but we have no idea what it actually is. And if you woke up tomorrow and the ground beneath your feet began to drift away from the rest of the planet, slowly at first, then faster, then so fast that continents moved apart like ice flows, you would not feel it. You would not see it. You would just notice eventually that the sun looked a little smaller, a redder, a colder. A year later, the stars you grew up looking at would be gone forever. And the night sky, the same one your great-grandparents looked at, would be a few thousand darker, emptier squares than it was the night before. That is the scale of the force we are talking about. By the end of this video, you're going to understand why the smartest minds on Earth are losing sleep over it, and why the universe, it turns out, may not be ending quietly. Imagine for a moment that you are standing on a quiet beach at night. Waves roll in. You cannot see where the ocean ends and the sky begins. Everything feels still. But the ocean is moving. The tide is coming in. The moon is pulling it. And if you had no knowledge of physics, you might think the sea was perfectly calm, perfectly still, perfectly at rest. That is how astronomers felt about the universe for most of human history. For thousands of years, every culture that ever looked up at the sky agreed on the same basic idea. The stars were fixed. The heavens were eternal. The universe was, on a large scale, permanent, calm, unchanging. Maybe it had a beginning, maybe it had not, but once it existed, it would, in some form, always exist. Then, in 1929, an astronomer named Edwin Hubble, working at a mountaintop observatory in California, pointed a new kind of telescope at a faint, smudgy object in the sky, and quietly shattered that idea forever. What Hubble saw, and what he proved through years of careful measurement, was that nearly every galaxy he looked at was moving away from us. And the farther away a galaxy was, the faster it was moving away. That was the shock. But the math behind it was the real shock. Every galaxy was not just moving away. They were all moving away from each other. This was not us at the center of something. This was space itself stretching. The universe, it turned out, was not static. It was expanding. And if you ran the film backward in your mind, all the galaxies, all the stars, all the matter in existence had once been packed into a single point, a beginning, a moment we now call the Big Bang, around 13.8 billion years ago. This was the first great discovery of modern cosmology, and it was strange enough on its own. But the strangest part was what the scientists thought would come next. If the universe began in a single moment, with all its matter flung outward in every direction, then gravity, the most familiar force in human experience, should be doing what gravity always does. It should be pulling things back together. The expansion should be slowing down. At first, you might still have galaxies flying apart because they had momentum, but over billions of years, the pull of all the matter in the universe should be dragging them back, like a ball thrown upward that is starting to lose speed against the pull of the Earth. The expansion should be decelerating. That was the prediction, and that was the assumption. For nearly 70 years after Hubble's discovery, every textbook in the world said the same thing. The universe was expanding, yes, but gravity was winning. The expansion was slowing. Eventually, gravity might even reverse it, pulling the cosmos back into a single point in a sort of reverse Big Bang, a moment that some scientists called the Big Crunch, the universe closing in on itself like a flower at the end of a day. Some models suggested this cycle might have happened many times before, with universes expanding, contracting, expanding again, like a cosmic heartbeat stretching across eternity. And then, in 1998, two teams of astronomers made a discovery so strange that the head of one of the teams reportedly called his colleague in the middle of the night to ask if he had made a mistake. The two teams were the Supernova Cosmology Project, led by a physicist named Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams were doing essentially the same thing. They were searching the distant universe for a particular kind of exploding star, a type Ia supernova, that they could use as what scientists call a standard candle, an object whose true brightness they already knew. If you know how bright something really is, and you can see how dim it looks from Earth, then you can calculate exactly how far away it is. Because dim means far, bright means close. That part is simple. What the two teams were trying to do was use these explosions to measure how fast the universe was expanding at different points in its long history. They were looking for deceleration. They were looking for gravity winning. What they found was the opposite. The supernovae in the distant ancient universe were too dim. If the universe had been slowing down the way everyone expected, then those ancient supernovae should have been a specific brightness, based on how far away they were. But they were fainter, significantly fainter, as if they were farther away than the math predicted. As if, since the light left those explosions billions of years ago, the universe had expanded more than it should have. The only way for that to be true was for the expansion of the universe to have sped up. Not slowed down, not stayed the same, sped up. Something was pushing, something was stretching space itself apart faster than gravity could pull it back. And this was not happening in some little corner of the universe. This was happening everywhere. The discovery was so shocking that the teams spent more than a year triple-checking their work. They reran every measurement. They reconsidered every possible error. They went looking for dust that might have dimmed the supernovae artificially. They checked for ways the original stars might have been different from the ones closer to us. Every alternative explanation they could imagine. And every alternative failed. In 1998, they published their results. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery. But the prize was not the headline. The headline was this: something was pushing the universe apart. Something we cannot see, something we cannot touch, something we cannot block, build a shield against, or push back from. Because it is not a force in the way gravity is a force, even though it acts like one. It does not come from any galaxy. It does not come from any object. It comes from everywhere. It comes from the emptiness itself. The scientists gave it a placeholder name. They called it dark energy, and they still do not know what it is. But here's the part that should keep you awake at night. When the cosmologists did the math on this new force, they discovered something almost embarrassing in its enormity. Dark energy is not a small thing. It is not a footnote. It is not a slight correction to an existing model. It is, by the best measurements we have today, approximately 68% of everything that exists in the universe. Let that number land. 68%. Stars, planets, black holes, galaxies, dust, gas, every object you have ever seen with a telescope, every photon that has ever reached your eye from the night sky, all of it, added together, accounts for less than 5% of the universe. Another 27% or so is something else we cannot see, something we have also given a placeholder name to: dark matter, the invisible glue that pulls galaxies together and keeps them from flying apart under their own spin. And the rest, the overwhelming majority of what is out there, is this thing we call dark energy. We are, as a civilization, standing inside a storm we can barely see, made mostly of something we cannot identify, with only the tiniest fraction of reality made of the matter we actually understand. That is where the story stood for about 2 decades. Dark. Energy was real. It was everywhere. It was acting like a kind of pressure embedded in space itself. And the simplest mathematical description of it, the one most scientists accepted as a working model, was something Albert Einstein had scribbled in his notebooks almost a century earlier, and then abandoned as his greatest mistake. Einstein, when he first wrote down the equations of general relativity back in 1917, realized that his math predicted a universe that could not stay still. Either it had to be expanding, or it had to be contracting. But in 1917, everyone, including Einstein himself, believed the universe was static, fixed, eternal. So he added a term to his equations, a kind of mathematical fudge factor, a constant that pushed outward just enough to balance the inward pull of gravity. He called it the cosmological constant. It was a number, a fixed value, and it represented, in his mind, the energy of empty space itself. Then Hubble discovered the expansion, and the universe was not static after all. Einstein could have dropped the cosmological constant entirely. According to the story most of us learned in school, that is exactly what he did, calling it the biggest blunder of his career, a momentary lapse he had patched over an unflattering truth. But the story is more subtle than that. The cosmological constant did not die in 1929. It was waiting. For 70 years it was waiting as one of the most elegant mathematical possibilities ever written down, hiding in a corner of physics, like a forgotten song left behind in an attic. When Perlmutter, Schmidt, and Rees discovered that the expansion of the universe was accelerating, the cosmological constant came back from the dead. It fit the data almost perfectly. If you imagine dark energy as a property of empty space itself, if you assume it pushes outward at a fixed strength everywhere and forever, then the math of the accelerating expansion lines up with what the supernovae were showing. This version of dark energy is the simplest. It is also the strangest. Because if dark energy is a property of empty space, then the more empty space you have, the more dark energy you have, and the universe is making more empty space every single second. Think of it this way. Imagine a sponge. The sponge is the universe. The water in the sponge is matter, the galaxies, the stars, the dust, the gas, all the ordinary stuff we can see. Now imagine that the sponge is expanding. It is getting bigger. As it gets bigger, the holes between the water are also getting bigger. And in this metaphor, the holes are dark energy. More sponge means more hole. More universe means more empty space. More empty space means more dark energy. And more dark energy means more expansion. And more expansion means even more empty space. The cycle feeds itself. The universe in this picture is not just stretching. It is stretching into a runaway, a slow runaway that has been going on for billions of years. And it will keep going. Forever, in fact. If dark energy really is a cosmological constant, this is the version of the future most cosmologists have lived with for the last 25 years. It is the version that wins Nobel Prizes. It is also, slowly and quietly, beginning to crack. Let me tell you why. There is a problem that has been bothering astronomers for almost a decade now, and it grows more serious with every new measurement. It is called the Hubble tension. And you do not need any physics to understand why it matters, only a single idea about how we measure distances in the universe. When astronomers point their telescopes at distant galaxies, they can measure how fast those galaxies are moving away from us. The number they get is called the Hubble constant. It is the number that tells you how fast the universe is expanding today, right now, in our neighborhood of space. But there are two very different ways to measure that number. The first way is to measure it locally. You look at nearby galaxies. You measure how fast they are moving. You compare that to how far away they are using standard candles, like those type Ia supernovae I mentioned earlier, or other bright landmarks, like certain kinds of stars called Cepheid variables, whose true brightness can be calculated from how regularly they pulse. From those local measurements, you build a cosmic distance ladder, rung by rung, out to the edge of what you can see. The second way is to measure it from the ancient universe. You look at the cosmic microwave background, the leftover glow of the Big Bang itself, which fills the entire sky at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. You measure the tiny temperature variations in that glow, which encode information about how the universe was behaving when it was only a few 100,000 years old. Then, you run that data forward through 13.8 billion years of cosmic history, using the best model you have of how the universe has evolved since then. At the end of the calculation, you get a prediction for what the Hubble constant should be today. For 20 years, both methods gave answers that mostly matched. The local measurement came out at around 73 kilometers per second per megaparsec. The early universe prediction came out at around 67 kilometers per second per megaparsec. The numbers were close enough that everyone called it a tie, a small disagreement that would probably go away with better data. But as the measurements got more precise, they did not move closer together. They moved further apart. By 2024, the discrepancy was over 4 standard deviations. By some estimates, it is approaching 5 or 6. In the language of physics, that is not a small disagreement. That is the kind of number you get when a measurement is almost certainly telling you that something is fundamentally wrong with the model you're using to interpret it. In plain English, the universe is telling us, with increasing confidence, that something we currently believe about how it works is simply not true. And one of the leading suspects is dark energy. Something is pushing, and we cannot see it, and we may not even be measuring it correctly. Then, in March of 2025, an international collaboration called the Dark Energy Spectroscopic Instrument, or DESI, which is a multi-year survey being run from a telescope in Arizona and stitching together the most detailed three-dimensional map of the universe ever made, announced the results of its first major data release. The DESI team had spent years measuring the positions of millions of galaxies. They were not just taking pretty pictures. They were carefully mapping how galaxies are clustered across the sky and how those clusters have changed over billions of years as the universe expanded. From that clustering, they could reconstruct with extraordinary precision the history of how the universe has stretched since the Big Bang. What they released in 2025 was, by their own description, the most precise measurement ever made of the expansion history of the cosmos. And the news was not what most cosmologists expected. If dark energy really is a cosmological constant, a fixed number written into the fabric of empty space, then the expansion history of the universe should follow a particular shape. It should match a specific mathematical curve. DESI's curve did not quite match. The data suggested, with a confidence the team described as tantalizing but not yet definitive, that dark energy may not be constant after all. It may be evolving. It may have been stronger or weaker in the past than it is now. The strength of the push, in other words, may have changed over time. This is a small thing to say about a huge thing. For 25 years, the simplest, cleanest, most beautiful explanation of dark energy has been a single fixed number embedded in the vacuum. Albert Einstein's old, supposedly abandoned idea dressed up in modern data. It has been the foundation of virtually every cosmological model we have published. It has shaped our understanding of what the universe is, what it contains, and how it will end. And DESI's results suggest that foundation may have a crack in it. To be clear, this is not yet a confirmed discovery. The DESI team themselves will tell you that their result is at the level of a statistical hint, not yet at the level of certainty. It is the kind of thing that physicists pay close attention to, because it might be wrong, but they do not sleep well at night because it might be right. Other instruments, other surveys, and other years of data will be needed before anyone can say with confidence whether dark energy really is evolving or whether we are being fooled by an unusually persuasive coincidence. But if the result holds, the implications are enormous. Because if dark energy is not a fixed constant, if it is instead something that changes with time, then the cosmological constant falls. And what replaces it must be something stranger, something physics has not yet named, something physicists have not yet imagined. And we would be standing at the beginning of an entirely new story about the fate of the universe rather than at the comfortable ending of an old one. But here is where the rabbit hole goes deeper. There is a number that physicists use to describe dark energy, and the exact value of that number decides how the universe ends. It is a number called W. It describes the relationship between the pressure of dark energy and its density. In the cosmological constant version of dark energy, W is exactly -1. That number, -1, is the holy grail of dark energy physics. It is the equilibrium value. It is what every measurement for the last 25 years has been trying to confirm. But what if W is not -1? What if it is slightly less than -1, like -1.05 or -1.1? Then you enter a regime that cosmologists call phantom energy. Phantom energy is dark energy that does not just push, it pushes harder and harder over time. Its strength grows the more the universe expands. And if that growth is fast enough, the math describes an ending that scientists have given a name that sounds like science fiction, and might as well be. They call it the Big Rip. The Big Rip is what happens when dark energy becomes strong enough to overcome every bond in the universe, from largest to smallest. It does not happen overnight. It takes a long time. Depending on exactly how phantom the energy truly is, the Big Rip could be tens of billions of years away, perhaps 100 billion, perhaps 200 billion years from now. Some estimates place it at around 200 billion years into the future, far past the present age of the universe, past the death of most stars, past the dying of almost everything we can see today. But the rate at which things would fall apart as the moment approached would be staggering. Roughly 60 million. Years before the final moment, galaxies at the edge of what we can see would begin to fly apart faster than their gravity could hold them together. Star systems in our own galaxy, including ours, would begin to drift. The Milky Way would lose its shape, its spiral arms stretching out. Like taffy, then tearing. By a few hundred million years before the end, no gravitationally bound structures would survive outside the cores of the largest galaxy clusters. The universe would become a churning sea of unbound stars, wandering without homes. By about 3 months before the end, the solar system itself would come apart. The sun would not hold the planets. The planets would not hold their moons. The Earth would not hold the moon. By 30 minutes before the end of everything, the Earth itself would not hold itself together. The mountains would lift, the oceans would lift, every solid would behave briefly like a liquid being pulled apart. And in the final fraction of a second, even atoms would be torn apart. The strong nuclear force, the most powerful force in nature, the force that holds protons and neutrons together inside the nuclei of atoms, would fail. Space itself, in the very last moment, would expand so fast that the distance between any 2 points would become infinite in a finite amount of time. That is one possible way the universe ends. It is not the only one, but it is the one that haunts me when I try to sleep. Something is pushing, and if it ever pushes hard enough, it does not just move galaxies, it unwinds reality itself, layer by layer, until nothing is left. But the Big Rip is not the only ending physicists have sketched out. There is also a quieter one, a colder one that most cosmologists currently consider the most likely if dark energy really is just a fixed cosmological constant, and the DESI hints turn out to be wrong. They call it the Big Freeze, or the heat death of the universe. If dark energy is fixed and the expansion keeps going forever at a steady rate, then galaxies will eventually fly beyond each other's visible horizon. Each galaxy will become its own island universe, unable to see any of the others, unable to communicate, unable to know that anything else exists. New stars will stop forming in about 100 trillion years when the last reserves of hydrogen and helium gas in galaxies are finally used up. The last red dwarf stars, the longest-lived stars in the universe, will burn out somewhere around 100 trillion years from now, leaving behind nothing but stellar corpses. After that, the universe will be full of dead stars, then black holes. Then, over timescales so long that even writing them down feels strange, the black holes themselves will evaporate through the slow leak of Hawking radiation, sending their mass back into the universe as the faintest possible whisper of heat, until nothing is left but a cold, dark, infinitely thin soup of elementary. Particles spread so far apart that the space between them is greater than the space inside them. The universe, in that version of the story, does not end with drama. It ends with silence, with nothing happening anywhere, forever, just an expanding dark, growing darker and colder by the second. But here is the thing. Even in the big freeze, dark energy is still there. It is still pushing, pulling apart what little is left, making the universe colder, darker, and emptier with every second that passes. Slowly, patiently, relentlessly. And in the Big Rip, it is the same force, just turned up. The two endings are not really different stories. They are two volumes of the same story. A story about a universe that is being slowly or quickly torn apart by something we cannot see, cannot touch, cannot measure with any instrument we have built so far. That is the part that gets me. Not the speed, not the drama. The fact that it is happening at all. The fact that the largest thing we know, the entire universe, is being shaped right now, today, by a force we have not yet learned to understand. Let me put this in terms you can feel in your body. You wake up tomorrow morning, the alarm goes off, you make coffee, you read a news story about something happening somewhere on Earth, you say goodbye to someone you love, you get in your car or your train or your bus, and you go to work and you do a job, and you come home and you sleep, and the next day you do it again. For your entire life, you have lived inside a universe that is being torn apart. While you slept, while you ate, while you fell in love, while you grieved, while you laughed with your friends, the space between galaxies has been growing every second, every heartbeat, every breath. Right now, in the time it took you to read this sentence, the distance between our galaxy and another galaxy, 2 billion light years away, has grown by something like 10,000 kilometers. That is 3 times around. The Earth, in the time it took you to blink. By tomorrow morning, those galaxies will be a little farther apart than they were today. By the time you are old, they will be measurably farther apart. By the time your grandchildren are old, they will be substantially farther apart. By the time the sun begins to die, in about 5 billion years, when it swells into a red giant and swallows the inner solar system, the galaxies beyond the Milky Way will be hundreds of thousands of kilometers farther apart than they are right now. This is not a metaphor. This is not poetry. This is happening. Measurably. Right now, today. And you, standing on a rock that is 4.5 billion years old, hurtling through space at 67,000 miles per hour around a star that has been burning for almost 5 billion years, will live a life somewhere around 80 years long. If you are very lucky, you will be born. You will live, you will die. And during that one short, sharp, blazing moment of consciousness, the universe around you will continue stretching apart, and you will not be able to feel it, hear it, see it, or do anything about it. That is the human scale of the problem. The deepest cosmic revelation ever made, and it is invisible to the only kind of eyes we have. Now, before we close, I want to ask you one thing, and I want you to answer it honestly, even if only in your own head. If dark energy is really tearing the universe apart, and if it has been doing so since before you were born, and if it will continue doing so long after you're gone, would you rather know that, or would you rather not? Would you rather look up at the night sky tonight and see the galaxies, knowing that they are flying away from each other forever? Or would you rather look up and just see stars? There is something almost unbearable about knowing both. Beautiful and unbearable. There's a strange kind of courage in admitting that. Most people, when they first hear about dark energy, want to feel small in the way that looking at a tall building makes you feel small. This is the other kind of small. The kind where you realize you are not just small compared to a galaxy. You are small compared to a process that has been going on for billions of years and will go on for trillions more. You are a flicker between two infinities.